Hello everyone. Today we want to talk about 12.3 Calculus in Polar Coordinates, the second part. In this lecture, we will talk about how to find the area enclosed by a polar curve. First, we will need something from pre-calculus. So let's take a look at the review. The area of the sector of a circle swept out by an angle theta with radius r is given by 1/2 r squared theta. So that means right here, if you have a circle with radius r, and let's say you have a sector, okay, and the angle is theta, then the area of this sector right here, okay, the area of this sector is 1/2 r squared theta. Okay, we will need this to establish our formula. So let's take a look at the ideas. We will use the slice and sum strategy. So right here, we assume that r equals f of theta. Okay, this polar equation is continuous. Okay, this polar function, okay, f of theta is continuous and non-negative. Okay, we assume that r, okay, is positive or 0. This interval from theta equals alpha to theta equals beta. So right here, the main idea is to use the slice and sum strategy. And we all know what to do. We want to divide this interval from angle alpha to angle beta. So that means this angle right here, okay, from angle alpha from here to here. So that means this part, okay, this part. We want to divide this interval into n subintervals evenly. Okay, and each subinterval has an angle of delta theta. So right here, delta, this triangle right here is the Greek letter delta. This means change in. So the change in theta should be beta minus alpha over n. Okay, so that means right here we will have n, okay, n angles right here. Okay, and in each subinterval, we will just pick a simple point. Let's call it theta k star. Okay, pick a simple point on this subinterval, and then we will evaluate this radius using the simple point. Okay, so f of theta k star, that will be our radius. Okay, so we can form a sector. And we want to use this sector, the area of this sector, as the approximation of the area enclosed by this curve. Okay, so right here we use the formula we talked about previously, 1/2 r squared theta. So 1/2. Okay, right here the radius is evaluated by f of theta k star. So this is the radius. Okay, 1/2 r squared times the corresponding angle, and notice that an angle right here is delta theta. Okay, so this will give you the area of this tiny sector. Okay, the area of the tiny sector. Okay, and we have n such sectors, so we will add all these areas together. So we use summation k star from 1 to n. Okay, so this means all these areas of the sectors. And notice that this is just an approximation. Because you can see that right here we have something we overcount and we have something we didn't count. Okay, so right here this is just an approximation. In order to get the accurate value, we will take the limit as n goes to infinity. So that will be our area. Okay, that will be our area. So right here, we know that the limit of the sum becomes the integral. And the integral of 1/2 r, so right here is f of theta, because r equals f of theta. R squared, 1/2 r squared theta, d theta, right here. Delta theta becomes d theta. That's the corresponding angle. So this tiny angle right here is your delta theta. Okay, and from alpha to some beta. So that will be the area formula, okay, enclosed by a polar curve. Okay, so in short, you have 1/2 radius squared times the corresponding angle. Okay, just like in the past, we say that if you want to find the area enclosed by y equals f of x and the x-axis, we say that the area is 1/2. The area is the integral of height times width. So right here from A to B. So f of x is your height, okay, dx is your width. So right here, f of theta is your radius, d theta is your angle. Okay. Now let's take a look at the box below. So in this box, we will introduce the case where we have two polar curves. So let R be the region bounded by the graphs of R equals f of theta and R equals g of theta, okay, between theta equals alpha and theta equals beta, where f and g are continuous. And right here, f of theta is greater than or equal to g of theta and greater than or equal to 0 on this interval. So notice that right here, you see that f of theta and g of theta are both 0. So that means, okay, they are non-negative. Okay, they are non-negative. And right here, you can see that f of theta is greater than or equal to g of theta. This means f of theta is farther away from the origin. So you can call f of theta the outside curve, okay? Because notice that f of theta represents the radius, g of theta represents the radius. So if this radius, okay, the radius on this graph is greater than the radius on this graph, that means this graph is, of course, farther away from the origin, okay? Just like before, if we have f of x greater than or equal to g of x, that means this graph is higher than this graph, right? Because they are y values. The y value of this graph is greater than the y value of that graph. Okay, so right now we have f of theta and g of theta. So that means the radius right here is greater than the radius right here. That is why f of theta is farther away from the origin. Okay, so basically you have a graph that might look like this. So we have this f of theta, okay, and that this is g of theta. Okay, so if you want to find the area enclosed by these two curves, you're finding the area in between. Okay, so basically we want to use the same idea. Right here, you notice that if we use the slice and sum strategy, we want to evaluate the area of this sector. So we want to use the area of the larger sector minus the area of the smaller sector. Okay, so just like the washer method we did before, right? The washer method we did before, we use the area of the larger circle minus the area of the smaller circle. So right here we have pi r squared minus pi r squared, right? And right here we have 1/2 r squared theta, okay, this theta, minus 1/2 r squared theta. Okay, the area of the larger circle minus the area of the smaller circle. Right here, the area of the larger sector minus the area of the smaller sector. Okay, so right here, our formula will become the integral 1/2 r. Okay, this is the larger r, larger radius, 1/2 r squared Okay, theta becomes d theta, so we will put that at the end. Minus 1/2, okay, smaller radius, square d theta, from alpha to beta. Okay, again, you know that I don't like this format because you might have a graph where f and g intersect. For example, this is your f, but this is your g, like this. Okay, so you can see that f is farther away from the radius right here, but g is farther away from the from the origin of the radius. I'm sorry. F right here, f has a larger radius. It's farther away from the origin. The g right here has a larger radius. It's farther away from the origin. So I preferred 1/2 r squared minus r squared d theta. Okay, and then all I need to do is to identify the larger radius and the smaller radius. It's okay? Okay, so let's take a look at some problems, some examples on the second page. Okay. So right here you can see that we want to find the area of the four-leaf rows. Okay, so this is what we call the four-leaf rows. R equals 2 times cosine 2 theta. So if you practice the practice problems on Canvas for the previous lecture notes, okay, you should be able to sketch this graph. Okay, right here, by using our formula, we know that we have to use. So let's make a quick review. The integral from alpha to beta 1/2 r square d theta. Okay, so right here, this is your radius r, and you notice that right here, you will need to put 2 cosine 2 theta right here. Okay, 2 cosine 2 theta right here. So that means you will need to square cosine, right? You will need to square cosine 2 theta. So that means eventually you will need to integrate cosine square. And we talked about this previously in, I believe, 8.3. Yes, 8.3 trig integrals, right? We say that if you want to integrate cosine square, there's something you need to do. So let's go back to page 1 and make this review really quick. To integrate cosine square and sine square, okay, in short, in general, we want to integrate the even power of cosine or even power of sine. We need to use half angle formulas. Okay, so right here to integrate cosine square, we have to write cosine square as 1 plus cosine 2 theta over 2. Okay, by using the half angle formula. And we will write sine square as 1 minus cosine 2 theta over 2. Okay, this is also the half angle formula. Okay, so let's go back to example 1. We want to find the area of the four-leaf rows. Okay, so of course we will set up my integral in this form. So 1/2 r, which is 2 cosine 2 theta, square d theta. Okay, now we will need to consider the bounds. Okay, so right here, if you practice the practice problems on Canvas for the previous lecture, you should know how to sketch the graph. And if you know how to sketch the graph, you should be able to find the bounds easily. Okay, now if you cannot remember how to do that, let's take a look at this. So apparently right here you have a symmetrical graph, right? This leaf is the same as this leaf, and this leaf is the same as this leaf, and the same as this leaf. Okay, so basically we can evaluate the area of one leaf and then multiply by 4, right? Now in particular, you'll notice that this leaf is also symmetrical, right? So basically you can evaluate half of the leaf and then multiply by 8. Okay, multiply by 8. The reason why we consider only half of the leaf, because it's easier. So you can see that right here, when your angle theta equals 0, Okay, let's plug in 0. Your radius is 2, so that means you have this point. Okay, so that means you travel from here okay, and then we want to find out when we have this point, when we have the origin. Okay, so you might want to set this equal to 0 to get 2 cosine 2 theta equals 0. So cosine 2 theta equals 0. So that means 2 theta should be pi over 2. And of course, dot, dot, dot. Okay, but notice that we just want the first one after theta passes 0. Okay, so that's pi over 2. That means your theta is pi over 4. Okay, so right here, this is pi over 4. Wow, that's a good spot. Okay, pi over 4. And of course, right here, cosine 2 theta equals 0 when 2 theta equals 3 pi over 2. So that means right here, theta equals pi over 4, you still have the origin. Okay, but we don't care about that. That is because we only consider the first half of the leaf. Is okay? So you can see that right here, this region is bounded by these two rays, from theta equals 0 to theta equals pi over 4. So we will integrate from 0 to pi over 4. Okay, so notice that this is half of the leaf. So this is the area of half of the leaf. Okay, so let's finish this. This will be 4. 4 times 1/2, that will be a 2. So let me put this 2 outside. Okay, so that will be cosine square 2 theta. Okay, and notice that right here, I will need to, this is cosine square. I want to integrate cosine square. So by using the half angle formula, it will be 1 plus cosine over 2, and that 2 and this 2 will cancel. Okay, so right here, we should have 1 plus cosine 4 theta. Okay, remember, you have to double your input. Okay, right here, double the input. Is okay? Okay, so it should be really straightforward. The integral of 1 is theta. The integral of cosine 4 theta is sine 4 theta over 4. Okay, don't forget the chain rule. Okay, right here, we want to evaluate from 0 to pi over 4. And you notice that when you plug in 0, this is 0, this is also 0. Okay, so let's just plug in pi over 4. So right here, we have pi over 4 plus 1 over 4 sine 4 times pi over 4, that's pi. Well, sine pi is 0, so we get pi over 4. Okay, so that means the area of half of the leaf is pi over 4. Therefore, the area of these rows is, okay, previously we say that we just calculate the area of half of the leaf. We need to multiply by 2 to get the area of a single leaf, and then multiply by 4 to get a whole area. Okay, so we multiply this number by 8 to get 2 pi. It's okay? Okay, so you can see that right here, we use this formula, 1/2 r squared d theta. Okay, 1/2 r squared d theta. And notice that for polar equations, okay, most of the time you will need to integrate cosine square or sine square. Okay, and in that case, we have to use the half angle formula. Okay, now I think in the past, students struggle on finding the bounds. Okay, because apparently if you consider the whole graph, okay, if you consider the whole graph, you don't know where to start. Okay, so right here we can use the symmetrical property of this graph, okay, to find the area of half of the leaf and then multiply by 8. Okay, that will be easier. Okay, and to find a bounds for this half of the leaf, we notice that right here we start from theta equals 0. Okay, and we want to find out when the curve will go back to the origin. So right here we set r be 0 to find the angle. So right here your region is bounded by theta equals 0, and theta equals pi over 4. Okay? So this is the case when we have a single polar curve. Now let's take a look at example 2 and see what happens if we have two copolar curves. Right here, we want to find the area of the region inside the circle r equals 1. Okay, so apparently this blue curve is the circle, right? Okay, r equals 1. And outside the cardioid, r equals 1 plus cosine theta. Okay, so outside this outside this red curve, the cardioid. Okay, so that should be this region right here. Right, that should be this region right here. Okay. So notice that right now we have two different curves. Okay, I want to find the area of this region. Okay, so of course we want to use the formula in the previous box. Excuse me. 1/2 outer radius. Okay, you can think of this as the outer radius or the larger radius minus the smaller radius. Okay, the inner radius. Okay, so right here apparently for this region, you can see that if you try to draw any ray, you can see that this radius will be larger than this radius, right? So draw any ray. Okay, so this radius will be greater than this radius. Okay, so that means in our region of interest, okay, this circle has a larger radius, and this cardioid has a smaller radius. Okay, so right here, if you want, you don't have to write it down, but I want you to know what's going on right here. So in our region of interest, okay, r equals 1 has a larger radius, and r equals 1 plus cosine theta has a smaller radius. This is important. For example, okay, so let's say we have a different problem. Okay, this time we want to find an area inside the cardioid but outside the circle. So that means this region. So if you draw a line, you can see that in this region, okay, in this region, the cardioid has a larger radius, while the circle has the smaller radius. Okay, so that's why it's really important. Okay, and that's why I don't like to use F and G, because sometimes this F might play a different role than G, right? Their roles might switch. Okay, so that's why I always consider larger radius and smaller radius. Okay, so right here, this is a different problem. Okay, let's assume we are finding this area. Then you can see that we want to switch these two. Okay. Okay, so that means right here we can use our formula. Okay, 1/2 larger radius square minus smaller radius square. It's okay. Okay, and then we want to find the bounds. Okay, again, this graph is symmetrical. Okay, this region is symmetrical. So basically, I can consider this portion to this portion, right? Consider this portion to this portion, and then multiply by 2. It's okay? Okay, now apparently right here, this theta is pi over 2, and this theta is pi. Okay, again, I say apparently is because when you sketch the graph, you can see that right here you have pi over 2. Okay, you have pi over 2. Okay, if you don't know how to find this, basically remember to find the intersection of two curves, you can simply set r. Okay, previously we set y equals y, right? Because that's because we have y equals f of x and y equals g of x. But now you should set r equals r. So we set 1 equals 1 plus cosine theta. Okay, so that means cosine theta is 0. Of course, theta equals pi over 2. And 3 pi over 2 is right here, so you can see another intersection right here. Does that make sense? Okay, so if you don't know how to find these bounds, okay, you can use this way. Okay, set them equal to each other to find the intersection. Okay, so right here you want to find the intersections. Okay, now if you know how to sketch the graph, apparently this is pi over 2, this is pi. Okay. Okay, so that means we want to integrate from pi over 2 to pi. Okay, from pi over 2 to pi. Now, some of you might be wondering, can I just do pi over 2 to 3 pi over 2 right here? Sure, of course, that will give you the same answer. Okay, but notice that if you do pi over 2 to pi, then you have to multiply by 2. Okay, because this is just half. Okay, this is just half of the, maybe I should label this is half of the area. Okay. Oh, oops. Now, if you do from pi over 2 to 3 pi over 2, you don't need to multiply by 2. Okay. Let's finish this. 2 times 1/2 is 1. So pi over 2 to pi. Okay, right here, I will have 1 minus. Okay, let's fold this out. This is 1 plus 2 cosine theta plus cosine square. Oh, oops. Okay, this is bracket. Okay, let's do it carefully. Then you have pi over 2 to pi. Right here, 1 minus 1, it's gone, and minus 2 cosine, and minus cosine square. Okay, so you notice that right here we have cosine square. So to integrate cosine square, we will need to use the half angle formula. Okay, so how about this? Let's pull this negative sign out. Okay, I don't want this negative sign to mess up with my calculation. So that's pi over 2 to pi. We have 2 cosine theta, and this should be 1 plus cosine 2 theta over 2. It's okay? So let's finish it right here. So we have negative. Okay, so let me integrate this. The integral of cosine is sine, so I have 2 sine theta. Okay, so you can basically split it into 1/2 plus 1/2 cosine 2 theta. Okay, and then integrate this and this respectively. So the integral of 1/2 is 1/2 theta. Okay, and the integral of cosine 2 theta is sine 2 theta over 2. Okay, don't forget the chain rule, but if you divide it by 2 and then multiply by 1/2, that's 1 over 4. It's okay? And from pi over 2 to pi. Okay? Okay, now right here, you can plug in upper bound. So sine pi is 0, sine 2 pi is 0. Oh, we have 1 over pi. So we have negative 1 pi over 2. What did I just say? I said 1 over pi. I'm sorry, 1/2 times theta. So pi over 2. Okay, we have pi over 2. So that's for the upper bound. Now you have to minus. Okay, minus, when you plug in the lower bound, notice that is a minus sign. So it should be a plus. Okay, it should be a plus. So let me plug in pi over 2 right here. Sine pi over 2 is 1. So we have a 2. Pi over 2 times 1/2, we have a 1 over 4. No, pi over 4. Sorry, I don't know what I'm thinking. Pi over 2 times 1/2, pi over 4, right? Pi over 4. Okay, and then pi over 2, plug in here, we have 2 theta, so that should be a sine pi. Sine pi is 0, that's good. Okay, so we have that. Oops. So let me write the answer right here. I'm sorry for a tiny space. I cannot do this here, otherwise it will mess up with my notes. Okay, so 2 plus pi over 4 plus negative pi over 4. So we should have a 2. And we have minus pi over 2 plus pi over 4, so that should be a minus pi over 4. Is okay? Okay, I believe that this calculation, you can do this calculation on your own. Okay, they are not too difficult. Okay, so I want to focus on how to set it up. Okay, so right here, first, of course, you want to know which region you are talking about. Okay, and once you find a region, you need to know which radius, okay, is larger. Okay, so if you don't know that, you can just draw any rate in your in your region, and you can see that the blue curve has a larger radius than the red curve. Okay, so once you know which radius is larger, you can set up the integral. Now to find the bounds, okay, basically you want to see, you want to find two rays, okay, that bound your region. Okay, so right here we still use the symmetrical property, okay, just like we did here. Okay, we found theta equals pi over 2 and theta equals pi, and then multiply by 2. Okay, and right here, if you don't know this is pi over 2, you can set r equals r to find the intersections. Okay, so you can see that pi over 2 is our intersection. Is that okay? Okay, there are more practice problems on Canvas. Okay, so please make sure you practice this. As I mentioned earlier, this is a very new concept. Okay, but you can see that the idea is not too difficult, right? We still use the size and sum strategy to find to create this formula. Okay, it's 1/2 r squared d theta. Okay, but it's very different from the area we used to evaluate before. Okay, because in the past we just consider the height times the width. Okay, but now we need to consider radius squared times the angle. Okay, so I believe more practice will benefit you. Okay, if you have any questions, please do not hesitate to let me know. Thank you.